I graded your tests. I already posted the grades online, and I'll give you your test back at the end of the hour. And then also, do you all know that today is Guacamole Day and Guacamole Day and Fibonacci Day? It was posted. I don't know if you saw it on the do you get emails from Gateway? I don't know if you do, but Guacamole Day and Fibonacci Day. The Fibonacci sequence is a mathematical sequence that goes 1, 1, 2, 3, 5. You add the two previous numbers. So 1 and 1 is 2, 1 and 2 is 3, 2 and 3 is 5, 3 and 5 is 8, 5 and 8 is 13. Anyway, that's the Fibonacci sequence. It has all sorts of interesting properties. So today on Milan, they're selling Fibonaccios. It's $3 for students and $5 for teachers. And then Guacamole Day, I think that's also today. A mole is a chemistry constant. It stands for 6.02 times 10 to the 23rd, which is 602 sextillion. So I'm not even going to write out all the zeros, but you can imagine million, billion, trillion, quadrillion, quintillion, sextillion. So it's 602 sextillion, which is the number of atoms or particles in a mole of a chemical substance. So it is Guacamole Day and Fibonaccios Day. So they're starting it at 11:30. But we'll be in class right then, so I figured we'll just take a slightly extended break. So normally we break from 11:50 to 12. We'll break from 11:50 to 12:05, and that gives everyone 15 minutes, just in case you want to go down there and purchase either some Fibonaccios or some guacamole. And then you can bring it back to class, and you can eat it here if you like. So that's today.
What are they saying?
Where is it?
What are they selling?
What are they selling? Nachos and guacamole. Yep. I'm sure it's going to be very tasty. And all the proceeds go to the Jimba Mathematical Lovers Scholarship, which is a scholarship Gateway hosts to give money to students. I think it's every semester. Okay. Well, folks, let's get started. You took your gifts for Chapter 3. Again, those are the last notes packets for the class. And I already posted the solutions for the first 3 of them. I still need to write up solutions for the last one. I'll post those online to you as well, through your email. And here we go. So, some questions. What is a definite integral? What is a definite integral? What does it find? Anyone want to field that one? What is a definite integral? What is it, Josue? Yeah, you do know. Go ahead.
Isn't it like the area or something? Like
it is.
Yeah.
A definite integral is where you're doing an integral, and then you actually have numbers right here, such that when you're all done, you end up with an actual number, like 120 feet squared, or something like that. So a definite integral has limits of integration, the upper limit and the lower limit, which means that you're actually capturing a certain area between 5 and 8. Whatever that curve may be, you're actually calculating an area, and the final answer should be a number, which represents the area. That's a definite integral. So what's an indefinite integral? What does it find?
Has no limit. Oh, what does it find?
Yeah, well, no, that's good. So indefinite. Indefinite means that there are no limits of integration. So there's no numbers there and there. So what are we finding that time? Just a formula. Right, so it's just a formula like 1/3 x cubed plus c. And we have that plus c because whatever that formula is, if you take the derivative of this, you should get back to this formula. And the derivative of this is x squared, and the derivative of a number is 0. So yes, this is the antiderivative. So a definite integral finds an area, whereas an indefinite integral finds an antiderivative, which if you then take the derivative, you should get back the same equation. Okay, what is the verbalization of the power rule? So let's say that you wanted to take the derivative of x to the n. What's the verbalization? You would, well, I'm doing the regular derivative, old school, regular derivative. Regular derivative, you would multiply by n and then subtract 1. Very good. That's the, wait, subtract 1. So yeah, that's the power rule. You multiply by the exponent and then subtract 1 from the exponent. What's the verbalization of the anti-power rule? Yeah, add 1.
I know how to write it.
Yeah, and then divide on what you get. Very good. Because we're going to continue to see this a lot. And it's at this point in the course that most students' brains go to mush. I say this in a very nice way. And you start doing these haphazardly. Like you're trying to do the derivative and you do the antiderivative. And then you're intending to do the antiderivative and then you do the derivative. Because these things are so close to each other. They're so close to each other that your brain starts substituting one for the other and then you get the whole problem wrong. So we want to be very clear on the process that these two, they're backwards, they're opposites. You might want to like tattoo one on your left hand and then tattoo one on your right hand. And that's okay. That wouldn't be cheating. That would just be a good memorization. Okay, so where are we? Today is November 7th. And we're going to do section 3-4. And then next week on Monday, so sad, we don't have class. It's not sad that it's Veterans Day. That's great. You know, say thank you to a veteran. But Monday there's no school. And then Wednesday we'll come back and we'll do section 3.5a. And then the next Monday, 3.6. And the next Wednesday, 3.6. Finishing 3.6 and 3.7. And then the next Wednesday, 3.7. And then the next time, November 28th, we'll review for a test. Gosh, where's Thanksgiving and all that?
It's next.
Thanksgiving is, oh, the 22nd. There we go. So Thanksgiving is in here. Thanksgiving Day. Okay. So yeah, we have class that day, and then we review for the test, and then we have our test. And then on December 5th, that's a Wednesday, we actually review for our final exam. I'll give you a practice final. I'll give you solutions for the practice final. Same as always. For a test, I'll give you the practice test as well as solutions. And then you'll come back on the 10th. That's a Monday. We're going to take our final exam in the same room, same time, so right here at 11 o'clock. And before you come to class that day, you'll take your course survey online. That'll be on Canvas. It's not posted yet, but that's what you'll do in order to come to class and take your final. Okay, so isn't this amazing? We're in the home stretch. We're almost done. I know that you're all very sad. Like, oh man, I don't want calculus to ever end. The good news is calculus never ends. Just this class ends, but calculus you can keep learning forever. Okay, Stephen.
Is it final exam? Probably a stupid question, but the final exam over all the chapters?
Yep, it's over everything. It's over all of chapter 2 and chapter 3. I'll probably pick out like 1 or 2 problems from each unit that we did.
Okay.
Okay. All right. Anyone else have a question? Okay. I have a joke here for you. This is maybe one of my more strange jokes. But first of all, you've all heard of the jokes of how many so-and-sos does it take to screw in a light bulb? I don't have an example one on the top of my head. Does anyone know a good light bulb joke that's not offensive? Like, what would be the word? I don't know, but I'm just going to tell you this one because I'm assuming you've all heard light bulb jokes. So, how many surrealists does it take to screw in a light bulb? Now, do you all know what a surrealist is? A surrealist is like artists like Dali. Dali draws those paintings of the clocks melting over a branch, or Dali, he has all these really straight parallel. I want to give you the maximum chance of appreciating this joke, because after all, it's a funny joke. So, surrealism, Dali. Here we go. So this is surrealism. You've probably seen this picture for sure, where the clocks are melting over the branch. But really, all of these, I mean, look how weird they are. It's not weird, it's surrealistic. Surrealistic is supposed to be like a dream. You know, so that's an example. Dali really started the whole movement. So, the joke then, how many surrealists does it take to screw in a light bulb? A fish. Yep, a fish. I'll just let you sit with that one.
Can you explain that one?
Yes. You're expecting a numerical answer, like 7 surrealists, or even 2.5 surrealists would be weird. But to be even weirder, they don't even answer the joke with a number. They answer with something totally nonsensical, like a fish, which makes about as much sense as surrealistic painting.
Okay, now that makes sense.
Okay, sweet. All right, so there we go. Just to give you another fun one, like as another light bulb joke, how many Zen Buddhists does it take to screw in a light bulb? 2. 1 to screw in the light bulb, and 1 not to screw in the light bulb.
Hey.
All right, well, here we go, folks. Section 3.4. Today we're looking at more complex examples of integrals. So before we even, yeah, here we go. Before we even look, you should all take out that sheet of lined paper where you wrote down all your formulas. You all theoretically have a sheet of lined paper where you wrote down all your formulas of all your different integrals. And I'm just going to go ahead and capture a summary of them right now. And that would be the anti-power rule. So the integral of x to the n dx is actually x to the n plus 1 divided by what you get. So there is the antiderivative of the power rule. We also have the antiderivative, or the integral of 1 over x. That one was just natural log of x. We also have the integral of e to the x, and that is equal to itself. So that's just e to the x. What else do we have? I would say that's really what we had as far as integrals. So, you know, now looking at this with fresh eyes, how many different types of integrals can we do? 3. So not a lot, right? This is what we practiced so far. We introduced 3 main types of integrals and how to do them. Now, keep in mind, to be fair, because we have the anti-power rule, we can also do integrals like 1 over x cubed, and we can also do integrals like the integral of the square root of x. So to be fair, we have a fair variety of different types of integrals that you can do. You can do any polynomial, you can do inverse functions, you can do square root functions, you can do 1 over x, which happens to be natural log of x, and you can do the natural, or the integral of e to the x. And then I also threw out another formula for us, which was the integral of natural log. And I'm hoping what I told you was x natural log x minus x. Is that what I told you before? Since you all have that sheet of lined paper out where you took all these notes, you can just quickly glance down and tell me, is that what I said?
Yeah.
Oh, good. Thank you, Diego. All right. So these are our formulas thus far for taking integrals. And what you'll notice from this list is there are all sorts of other types of integrals that we might want to take. Right? Not every formula in the world matches one of these. So we're going to learn a new method today, which is basically how to do the chain rule backwards. And I think we'll just dive right in and try one. So first, let's remind ourselves what the chain rule looks like. So, you know, everybody, we're right here, and we're going to do the problem for number 1 over here. So why don't you just come over here and make a little reminder to yourself about the chain rule. Because what we're about to do is to take the integral of the result of a chain rule. And so right at the top I said consider the chain rule. So let's try a chain rule. And in fact, let's remind ourselves how the chain rule works. Let's go ahead and use this guy right here. We might as well. No, actually, I take it back. That's not a very good example. Let's do an actual chain rule. Not that one. So the actual chain rule, let's try an example like this. If we had f of x equals x squared minus 3 to the power of 5. There we go. We're going to do the chain rule on this. So who remembers the chain rule? You have an inside function, x squared minus 3. You have an outside function to the power of 5. So if you recall, the inside function is x squared minus 3. The outside function is something to the 5th, right? So what's the verbalization of the chain rule?
Or just get the outside, yeah, and then
Leave the inside alone.
Is it plus or minus?
Multiply
Multiply.
by the derivative of the inside. So everyone remember, chain rule states take the derivative of the outside, leave the inside alone, and then multiply by the derivative of the inside. So let's do it. The derivative would be, take the derivative of the outside, so that would be 5 something to the 4th, that's the derivative of the outside, leave the inside alone, and then multiply by the derivative of the inside, and the derivative of x squared minus 3 is just 2x. All right, so that's the chain rule. I don't know why the door is locked. Now it's unlocked. All right. Now what we notice here, folks, is that it's just based on our knowledge of what integrals do, right? If you take the integral and then take the derivative of that answer, it should take you back to the integral. Both ways, right? So if you take a function and you take the derivative and then you take the integral of that, you just get your function back again. Or if you take a function and you take the integral, and you take the derivative of that, again, you should get your function back. So whichever order you do it in, if you take the derivative of the integral or integral of the derivative, they cancel each other out, and you get back to where you started. So I'd like you to just take a look now. Given this example, what would be the integral of 5x squared minus 3 to the 4th times 2x? What would be the integral of that? Exactly, just the original problem. X squared minus 3 to the power 5. Right, because they should lead to each other. So, whereas if I take the derivative of x squared minus 3 to the power 5, I should get 5x squared minus 3 to the 4th times 2x. There. I would take a good gander at this. That taking the derivative of what we did, you do the chain rule, and therefore the integral of the chain rule would take us back to the original function. And that's what we're looking at today. We're simply going to do chain rules backwards. We're simply going to do chain rules backwards. And that's what this method is called, U substitution. It's called U substitution, but we're really just going to do the chain rule backwards. Let's just do one more example. Let's say I came up with another chain rule. So we're going to say, what if our function was just something basic? Oh, I know, the natural log of x squared plus 4. So this is the chain rule, because you have an inside function, x squared plus 4, you have an outside function, natural log. So the inside function is x squared plus 4, and the outside function is the natural log of something. So remember, the derivative of x squared plus 4 is just going to be 2x. And the derivative of natural log, what's the derivative of natural log? 1 over x, or whatever 1 over the argument is. So that becomes 1 over the argument. So take a look. If I have this natural log of x squared plus 4, the derivative of that would be, take the derivative of the outside function, that means 1 over something, leave the inside alone, x squared plus 4, and then multiply by the derivative of the inside, which is 2x. So everything that you see right here, if I were now to take the integral of that, the integral of 1 over x squared plus 4 times 2x, what would that integral be? Natural log of x squared plus 4. Because it's just going to reverse the process and take us back to where we started. So in other words, one thing that you might also take a note of is that the integral of the derivative is equal to the original function. That's a very powerful idea. If you take the integral of the derivative, it's simply the original function. Okay, that's my introduction. Let's go ahead and do this method called U substitution, and you'll see what to do. So first of all, everyone, let's take a look at number 1. Now, first of all, just to verify, do I have everyone's full attention? Because I see a couple of you are looking at your computer screen. I don't know what's on the computer screen. If it's a good method of, a good episode of Star Trek, I would understand. But everybody, let's watch this method. All right, so take a look here. We have the integral of x to the 5th times x to the 6 minus 7 to the power 47. Just looking at that right now, what would you say the inside function was? Which part of all that is the inside function? Yeah, the x to the 6 minus 7, right? Almost always when we do this method called U substitution, you want to find the inside-most function and call that u equals x to the 6 minus 7. We use the letter u because we've already used a lot of other letters for other purposes. And this method is called U substitution. If you go anywhere in the world and do calculus, they're going to call this method U substitution. You don't use a regular u, you use a cursive u. Okay. I'm sorry, I kind of skipped one thing. Do we already know how to take this integral? Do we have a rule for that integral already? It's certainly not the natural log. It's certainly not e to the x. It's not a fraction. Is that a simple power rule? It almost looks like a simple power rule, except for the fact that it's a product. We have something times something. So we, in fact, don't know how to do this integral. We don't have a method currently. The tools we already had, we didn't have a way for doing this integral. you can't just do the integral of each individual part one at a time and just say, oh, there we go. Hey there, Brendan. Okay, so here we go, folks. You find the insidemost function, and you say, let that be u. Now what we're going to do is take the derivative of both sides of this function. All right? Now, when we have a single letter, like u, and we want to take the derivative of it, in the past we would have said, oh, the derivative of 1u is simply 1, right? That's what we would have said in the past. Whereas right now, we want to treat both of these as though they themselves are potential functions. Like they are potential functions that need to be derived. So what we'll do instead is the derivative of u, we're going to call du. And we're saying that's the derivative of u. So whatever u is, we're just going to treat the symbol du as the derivative of that letter. Furthermore, when we do the derivative of x to the 6th, first of all, notice the derivative of 7 is 0, so we can ignore that part. But the derivative of x to the 6th would be 6 x to the 5th, and then at the end of that we write dx. We're taking the derivative of x to the 6th, but then we're considering the possibility that x itself is a function, and so we're multiplying as well by dx. That's the chain rule in and of itself. Like let's just say you had the function f of x to the 6th. The chain rule would say take the derivative of the outside, so that's 6 f of x to the 5th, and then multiply by the derivative of the inside, which is f prime of x. So if you were taking the derivative of a function, you'd have to do the chain rule and multiply by the derivative of that function, and that's what we're doing here. When we do the derivative of x to the 6th, we do the normal power rule, so 6 times x to the 5th, but then we multiply, the chain rule, multiply by the derivative of the inside, and the derivative of x is just dx. Now, folks, this is brand new. I'm hitting you with this fresh. You've never seen this before. Right now, for the first time ever, I'm saying that if you take the derivative of a single letter, you call the derivative du. Or if you take the derivative of x, you call that dx. We're temporarily forgetting about the fact that the derivative of x would simply be 1, or the derivative of u would be 1. We're saying, actually, we need to keep track of those variables. And when you take the derivative of a single variable, you write du, or dx. Okay, one last thing we want to do here, folks, is anytime you end up with a coefficient, this is going to seem arbitrary at first. Anytime you end up with a coefficient, you want to divide it over to the other side. So we're going to move the 6 over to this side with the du. And instead of dividing by 6, like don't write this down. If you were to divide out the 6, it would look like that. And that wouldn't be very pretty. I don't want du over 6. I want 1/6 du. So remember, how do you get rid of a coefficient? You multiply by the reciprocal. So I'm going to multiply both sides by 1/6. That will cancel out that one. And I'm left with 1/6 du equals x to the 5th dx. Okay, I now have 2 facts. Now, right now, you might be wondering, Mr. G, what on earth are we doing? Well, I'm showing you a new method you've never seen before. And this is the front work to get ready to do that integral. The front work is to find the insidemost function and call it u, and then take the derivative of that and move your coefficient to the other side. So now we have 2 statements here. And what we'd like to do, now let's do the integral. I'm going to take my integral, which was x to the 5th, write it down with me again, x to the 6th minus 7 to the 47 dx. And I want to rewrite this entire integral in terms of the letters u. So for instance, right here, this x to the 6th minus 7, what can I put there instead of x to the 6th minus 7?
1/60.
No, I can just put u. I can just put the letter u, because we have that equation there. X to the 6 minus 7 is u, so I'm just going to write the letter u. So that's u. Now what about this x to the 5th and the dx? Pretend they're sitting right next to each other. Where do I have an x to the 5th and a dx? Right here. So what can I replace the x to the 5th and the dx with? 1/6 and du. I can replace them. So right here, for the 1/5, I'm sorry, x to the 5th, I'm going to put 1/6. And for that dx, I'm going to put du. And what I'm doing here is I'm just replacing everything. I'm replacing every part of this integral with something that I had over here. So now let's write down our new integral, folks. Our new integral is simply 1/6 u to the 47th du. And again, let's just sit and look at that for a second. Here's the big idea. We're looking at an integral that we have no idea how to solve. Because it's the product of x to the 5th times this thing to the 47th, we do not currently have a rule for doing this integral. We don't have a rule for doing this integral. But we were able to find the insidemost function, call it u, and then take the derivative of that and call that 1/6 du equals x to the 5th dx. And I replaced the x to the 6 minus 7 with the letter u. I replaced the x to the 5th dx with 1/6 du. And now I have an integral, which I say we can do. This integral we can actually do. How do we do this integral? It's just the anti-power rule. This is just u to the 47th being multiplied by a constant. How do you do the anti-power rule? You
Add 1.
add 1 and divide by what you get, right? So I've got a 1/6 u to the 47th. U to the 47th, I add 1 and divide by what you get. So everybody go ahead. Add 1. So this will become u to the 48. And then divide by what you get. So what's 1/6 divided by 48? That might look a little nasty. 1/6 divided by 48. I hope that we can all memorize the quick way of doing problems like this. When you say, and everyone you can just watch, when you say 1/6 divided by 48, that's the same as 1/6 divided by 48 over 1. And dividing by a fraction is the same as multiplying by the reciprocal. That's really 1/6 times 1 over 48. And the answer is really 1/6, 1 over 6 times 48. So in other words, if you're going to divide by 48, where do you put the 48? In the numerator or the denominator? In the denominator. That's the quick way. That's the quick way. Instead of thinking to yourself, what's 1/6 divided by 48, and you have to follow this whole chain of reasoning, the point is you just put the 48 in the denominator. And that's how you do that quickly. So what's 1/6 divided by 48? You just put the 48 into the denominator with the 6. Okay, well, folks, we just did it. We just did the integral. So I no longer use my integral symbol. And in fact, this is not a definite integral, so there's no evaluation line. We're simply done. This is the antiderivative. This is the integral. I'm going to clean it up and say that 6 times 48 is really what? Is it 288? U to the 48? So that's my answer. The integral is 1/288 u to the 48. Let's just check that to be sure. Yep. And I would say we're done except for we're in the variable u. We don't want to be in the variable u. We want to be in the variable of x. So my last step is simply to substitute back in the x to the 6th minus 7. So our actual answer is 1 over 288, parenthesis, x to the 6th minus 7 to the power of 48. And I claim that that is the integral of this original problem. Now, if that method felt a little clunky to you, that I don't blame you. The first time through this, there's so many moving parts and pieces, it might feel a little confusing. But we're going to do more practice with the u substitution. So we'll see it a few times. But that was the basic method. We took this integral that we weren't sure how to integrate. We found the inside function, replaced it with the letter u, took the derivative of that function to get 1/6 du equals x to the 5th dx. We replaced all the parts and pieces of this integral to get a simpler integral, which we were able to simply take the antiderivative of. And then when we're all done, we replace back with what u is equal to. Now you might look at this. Go ahead, Bata.
The power of 5.
What about what power of 5?
The x power of 5. We just replace the x now with power of 5. So we don't use anymore?
We replaced both of those. This x to the 5th and this dx got replaced by 1/6 du. So this x to the fifth and that dx right here got replaced by 1/6 in du. I don't know if I just answered your question. Now, folks, mathematically, we claim that this is the integral of this. How do we check that this really is the integral of that? Yeah, you take the derivative. So everybody, keep writing. Let's take the derivative of this. Let's take the derivative of this. This is a chain rule. We have an inside function and an outside function. So how do we take the derivative? Everybody, we take the derivative of the outside. So we're going to multiply the 48 out front. Derivative of the outside. There's that. That's the derivative of the outside. I multiplied by 48. 48 times the fraction 1 over 288 is 48 over 288. I subtracted 1, so I just did the power rule. Leave the inside alone. And then what? Multiply by the derivative of the inside. The derivative of the inside is 6x to the fifth. Did I do my derivative correctly? That's it. So now we can clean this up quite a bit. We can bring the 6 over with this fraction. So that becomes 6 times 48 all over 288. We can bring the x to the fifth out front as well. And then we have the x to the 6 minus 7 to the 47. Now, we already saw what 6 times 48 was. What's 6 times 48? 288. And 288 over 288 is 1. And so what are we left with? Is that the original problem? It is the original problem. And therefore, this integral is the correct answer. Okay, that was a doozy. We should all already take a nap and eat some Fibonaccios and some guacamole. But we're going to do at least 2 more of these before we go take a break. You don't always have to finish the problem by taking the derivative to see that you get back the original. But that is a best practice. I mean, you just did all this effort to get the answer. You might as well take the derivative and check to make sure you get back the original, because that's the only way you really guarantee that you got the right answer. So that's our first one. I'm going to leave that up on the board while we move on to try the next one, which I'll do over here. So we'd like to do the integral of x to the fourth e to the 5x. So this is where we are now. We're doing number 3. My numbers bounce around a little bit. I put the numbers into the packet in the order in which I wanted us to do them. So we'd like to take this integral. First of all, notice we do not currently have a formula for doing this integral. Sure, we can do the integral of x to the fourth, and sure, we can do the integral of e to the 5x, but we can't do the integral of those two things being multiplied together, which is what this problem is. Yeah?
On your packet it says ex to the power of 5.
Oh, do I not have the x to the fourth, e to the x to the fifth.
But looking into the
You put x5,
Oh.
not 5x.
X.
Oh.
Oh, how weird. Oh. Thank you. I just wrote it down. The packet is correct. I am wrong. Thank you. My brain saw that and I just wrote it down as 5x. Okay, there's our integral. That's the integral we want to take. And once again, what I want to call to your attention is that this is the product of 2 functions that we do know how to take the derivative of. Integral. I could take the integral of x to the fourth. If I just took the integral of x to the fourth, I would get the answer x to the fifth over 5. But if I just took the integral, well, I can't just take the integral of e to the x to the fifth. Well, let's just pretend we could. I could do the integral of these 2 things separately, but together, we're not sure. So we have to use u substitution. So the first step of u substitution is to find the innermost function and call it u. What's the inside function here? What do you think would be the inside function? What part is inside of something else? It's the x to the fifth. X to the fifth is the inside function because it's inside e to the. Therefore, we're going to define u is x to the fifth. So again, whenever we do u substitution, you look for the inside-most function that you can find. X to the fourth is not inside of anything. E is the outside function. X to the fifth is the inside function. And you let u equal the inside function that you find. Now let's take the derivative of both of those. The derivative of u is just called du. The derivative of x to the fifth is 5x to the fourth, but then you multiply by dx. That's the chain rule on x. And we're always going to move whatever coefficient we end up with over to the other side. So 5 on this side becomes what on this side? 1/5 du equals x to the fourth dx. Now, I want you to notice that I now have all the parts and pieces of this integral. I have an x to the fourth, I have an x to the fifth, I have dx. So now I'm just going to replace all these things. My x to the fifth, I get to replace with u. My x to the fourth and dx, I get to replace with 1/5 du. And e is simply part of my integral. So now replace everything. So I have e to the u, and then my x to the fourth dx gets replaced with 1/5 du. Does everyone see that substitution that's taking place? No, really. Does everyone see how we just substituted all that? We're saying that 1/5 du is equal to x to the fourth dx. So I replace the x to the fourth bit with the 1/5 bit. I replace the dx with the du. And I replace the x to the fifth with the u. And now I just have this integral. And this integral, I claim, we can do very easily. We all know how to do this integral. You can bring the 1/5 out front. And what's the integral of e to the u? It's just e to the u. Yeah, the integral of e to the u is just e to the u. So this integral is simply 1/5 e to the u. So you'll notice my integral symbol went away because I took the integral. And now that's it. That's the answer. That's the answer except for the fact that we're still in the variable u. We don't want to be in the variable u. We want to be in the original variable of the original problem, which was x. So now the last thing we do is we just replace the u with what we know u is equal to, which is 1/5 e to the x to the fifth plus c. And that's the final answer. And that's u substitution. U substitution allows us to take the integral of an expression that is the product of simple integrals that we would know how to do on their own, but we don't know how to do when they're being multiplied together. Now you might ask yourself, is this answer correct? Is this answer correct? How do we find out if this answer is correct? You take the derivative. So let's try it. If I take the derivative of this is a chain rule, e to the x to the fifth. The derivative would be, take the derivative of the outside function. The derivative of e to the anything is still just e to the anything. Keep the inside the same. And then multiply by the derivative of the inside, which is times 5x to the fourth. So now what do we have? We have 5 and 1/5. They multiply together to equal 1. And what I'm left with is just x to the fourth, e to the x to the fifth. And is that the original problem we started with? Yeah. So that guarantees us that this answer is correct. So what do we notice so far? What types of integrals are we taking? Like even just look at this next one we're about to do, number 9. What kind of integrals are we looking at? Well, it is the opposite of the chain rule, but technically we're looking at a product. So if you wanted to, you could call this the integral product rule, because we're looking at the integral of a product of two functions. Not any product, just a special product that you're able to use U substitution. Okay.
Number 9 or 5?
What is your paper called?
9, but it's.
Oh, the next one on the sheet is 5? Will you all just turn the page and go to number 9? Sorry, flip the page and go to number 9. I just realized that 9 is so close to number 3, I thought we might as well do it next. Sorry. Oh, is that really number 9 in your packet?
Yeah.
Okay. So once again, we want to take this integral, and you notice it's the product of a power function times an e function, and you want to look for the insidemost function. So what's the insidemost function? X to the 7, because that's inside the e to the something function. So we'll go ahead and call that x to the 7th u. Now watch how I'm doing this, because I want you to show your work the same way. The problem is here. We go over to the right, and we say, okay, u is equal to x to the 7th. This is like scratch work, but necessary. So you have u equals that. Now I take the derivative of both sides. So the derivative of u is du. The derivative of x to the 7th is 7x to the 6th dx. So you're doing the normal power rule, but you're writing dx at the end of it. And now we move the 7 over to the other side, which hopefully we all just have this memorized, that when you divide the 7 over, it becomes 1/7 du equals x to the 6th dx. Now I'm hoping third time's the charm here. You have an x to the 6th piece, there it is. You have a dx piece, there it is. You have an x to the 7th piece, there it is. So now we can term by term replace everything in this integral with our new u variable. So instead of e to the x to the 7th, we simply have e to the power of u. And instead of x to the 6th dx, we have 1/7 du. That process that we just did right there is called u substitution. What is the purpose of u substitution? It takes an integral that is the product of two functions that we don't know how to integrate, and it replaces that integral with an easier integral that we do know how to integrate. So now that I have 1/7 e to the du, that's simple. I bring the 1/7 out front, and now I'm just doing the integral of e to the u du, which is one of our formulas. The integral of e to the x dx is just e to the x. So the answer is 1/7 e to the u. That's the integral in the variable u. So our last step is simply to replace u back with what we knew it to be, which is 1/7 e to the x to the 7th plus c. And we claim at least that that is the integral of the original. That's the integral of the original function. And it can't hurt to ask again, how do we know that's the right answer? What do we do if we want to check? Find the derivative of that. And if the derivative of this is this, then we know that we did the correct integral. So I'm gonna take the derivative real quick. This is e to the x to the 7th, so the derivative of the outside, so e to the x to the 7th, e to the anything is still e to the anything. Leave the inside alone, and then multiply by the derivative of the inside, which is 7x to the 6th. The 7 and the 1/7 cancel out, and we get x to the 6th, e to the x to the 7th, which is the original problem that we started with. So that is the integral. So that method that we just did is called u substitution, and it only gets more exciting from here. So let's see. My phone is about to go off, which means we can go get for the nachos and guacamole. But let's just go ahead and glance back at number 5 now. Look at number 5. Hold on, we won't say anything about this, other than just start the problem. We'll just write down u. What's the insidemost function here? T plus 1. So we know u is equal to t plus 1, and then we take the derivative of that. So that's du equals the derivative of t is just dt. And that's the u substitution component. We looked for the insidemost function, called it u, and then took the derivative of both sides. Keep in mind, folks, this new rule that we're learning today is that the derivative of a letter is d in front of that letter. So the derivative of u is du, the derivative of t is dt. The derivative of 1 is still nothing. And now we go through and we replace everything that we see. So what do we replace it with? We still have a 7. We still have something to the 9th. But what does t plus 1 get replaced by? U. And what does dt get replaced by? Du. Not because dt is equal to du. So we have this. And how do we rewrite that in a user-friendly form? This is really 7 over u to the 9th, but we have to push the u to the 9th up to the numerator. So this is the integral of 7u to the negative 9th. And we can do that. That's just a normal anti-power rule. We'll finish this problem, then we'll go get nachos. So how do we do the normal anti-power rule? We add 1 and divide by what you get. So I'm going to add 1 and divide by what you get. And the integral symbol went away because we just did the integral. And this is the answer, except for the fact that we're still in the u variable. We need to replace u with t plus 1. Well, actually, we can make it a little easier on ourselves by pushing that 8 into the denominator first. So this is already a fraction, 7 over 8. Where does the u to the 8th go? In the denominator, so that it's a positive u to the 8th. And now finally, once we're all done manipulating and simplifying, we just replace u with t plus 1. So we end up with 7 over negative 8 t plus 1 to the 8. Plus c. And we claim that that is the integral of the original problem. We claim that. We still have to check. We would still have to take the derivative of that and see if we get this back. And I'll go ahead and take the derivative of that. If I have negative 7/8 times t plus 1 to the negative 8, I pushed it back to the numerator, and I take the derivative, I multiply by negative 8, so that's negative 7 times negative 8 all over 8 times t plus 1 to the minus 1, I subtract 1, negative 9, the 8's cancel out, the negatives cancel out, and I have 7 t plus 1 to the negative 9, which is really 7 over t plus 1 to the 9. And is that the original problem? Yeah. Yeah. So this is u substitution. And this is a great place to stop. We've now introduced our brain to this idea of u substitution. The time is 11:52. Let's take 15 minutes. That'll take us out to 12:07. And let's go get some Fibonacci clock.